So PPO is a non-policy algorithm which will iteratively update the policy parameters, and let's say at some point of time theta k is the parameter that we have for the policy. Okay, that is the policy currently we have is pi theta k. Okay, and let's say a pi theta k or a pi theta k is the advantage function that you have currently. So do you remember what is advantage function? What is advantage function? Do you remember? Yes or no?
So it tells how good the current action is as compared to estimate of the policy.
Yeah, generally that's what it is. So what is mathematically?
QSA minus.
Yeah. So this is q pi theta k of s comma a minus v pi theta k of s, right? So how can you write v pi theta k in terms of q pi? This is expectation over a from theta k q of s comma a. I can write it like this, right? Q pi. The value function is nothing but expected value of the q function, where the action is sampled according to your policy pi. So if you look at this definition of advantage, what is it telling? It's telling whatever that student has told about the intuition of advantage. So q pi theta k is the return that you will get if you take action A in this time step, and this is the return that you will get if you choose the action according to the current policy, right? This is the average return that you will get if you choose the action according to your current policy, and this is the return that you will get if you deviate from this policy and take a different action. So if this deviation is good, that is, if this deviation is good, this will be positive, right? Because that means the current action A is better than the average action that is suggested by the policy. If this will be negative when the deviation is bad, right? If this is negative, that means that this action is bad than an average action or a typical action that is suggested by policy pi. So let's say you have some current policy pi theta k, and you somehow estimate this advantage function. We know how to estimate action value function and value functions, right? We have seen some methods, right? In DQN we are doing, everywhere we are doing, right? We are estimating the Q function. You just parameterize the Q function and do a gradient descent on top of it, right? So you know how to find, similarly we can find the advantage function also. You can represent the advantage function using some neural network, and you learn the parameters of the advantage function by interacting with the environment using your current policy. Okay, so you estimate the advantage function of your current policy, and based on that you want to decide how do you want to update your policy. Okay, so one meaningful way to update our policy is this. So let's say I want to find the new policy parameters, which is represented by what? Our current policy parameters are theta k. What will be my new policy parameters? Theta k plus 1. So we want to find theta k plus 1 in this way. So let's say this is my new parameter theta. My new parameter theta should be, let's say if for some action A, the advantage is positive, then what do we understand about, what do we infer from that? Let's say you have some policy pi theta k currently, and for that policy the advantage function for some action A is positive. Okay, then what do we infer from that?
So
preferable action.
It's a good action compared to your current policy, right? So then in the next policy, what do you want to do?
You give more probability.
You increase the probability of that action, right, than what you are currently having. So this is exactly that, right? What is this term telling? What is the probability of taking that action in your new policy? Like if theta is the new policy, which policy parameter which you are going to find, this is telling what is the probability of taking that action in the new policy. That should be more than your current policy or less than your current policy. So first of all, you have to compare with your current policy, right? So how do you compare? You just take the ratio. Okay. If it's a good action, that means the advantage is positive, then what do you want this ratio to be? High or low? If advantage is positive, you want this ratio to be high. If advantage is negative, then what do you want this ratio to be? You want this ratio to be less, right? So how can I write that as an objective? Can I write it like this? Now this is for a given state. This is for a given state, right? For every state you have to deal with this, right? So for what you can do is you can take an expectation over s comma a with respect to theta k. You just look at, for every s comma a pair you have to deal with this, right? So you want to maximize this. Is this convincing? All that I am trying to say is if advantage is, when will this objective get maximized? If the advantage is positive, if advantage is, let's say, +2 for some s comma a pair, then you will try this. Since you are maximizing this ratio will try to go as high as possible, correct? Then only the whole term will get maximized, right? But let's say the advantage is negative for something, okay, for some s comma a pair, then if you are trying to maximize the overall product, what will this try to do? What will happen to this term in this maximization process? It will go down. So that's what we also want, right? We want it to go down whenever it is negative, and whenever it is positive we want this term to go up. So if I just maximize the product of these two terms, then that is what is effectively happening, right? Because whenever it is positive it is trying to maximize this term, whenever it is negative it is trying to minimize this ratio, okay? So for good, but you have to be careful when you are dealing with this objective, in the sense that, let's say there are only two actions, let's call them left comma right, okay, and in a particular state S, let's say one of them has positive advantage, let's say the advantage is +2, the other, in a given state, let's say maybe a of s comma l is +2 and a of s comma r is -2, okay. Then if I just try to maximize this objective, okay, so let's say both of them have half probability right now, okay, pi of L given S is half and pi of R given S is also half according to my current policy, okay. So then if I try to forget about this expectation, let's say you are dealing with this particular state S comma a pair, so then for this S comma L pair you have positive thing. So then if you are trying to maximize this product, what will you take as your new probability of left? In the updated policy, if you are just trying to maximize this product, what will you take as the new probability of going left? 1, right? Because why do you want to take anything less? Because you are trying to maximize this thing. So this part is 2 + 2 and this is half, which are constants, Like what is the objective variable? What is the running variable here? Theta is the only running variable, and this is plus 2, this is fixed, and this is half. Now the only thing in the objective left is pi theta of a given s, that is left given s. Then when will this get maximized? You make it 1. And what about this? What will happen to r? So here you have minus 2 for r, and this is half. The only running variable you have is theta. And when will this get maximized, this product?
0.
You make it 0. So that means if you take this as your objective, it will try to make big jumps in your policy. It will try to either fully favor one action or like pull down one action totally. So you don't want such drastic things to happen in your updates, right? You want the updates to be in a gradual manner, because this is not the exact action value function. This is not the exact advantage function, right? This is an estimate of the advantage function. Based on this, you don't want to take such drastic steps. Is it clear what I am saying? So PPO, while it is interested in maximizing this objective, it will ensure that there is some limit on how much you can update your policy. Okay, you should not suddenly change your policy to something very different. Okay, so there are a lot of algorithms which will try to do something like this. One such algorithm is called TRPO. What is called trust region policy optimization. So at a very high level, what it is telling is, if you have some policy currently, the next policy should not be arbitrarily different from your current policy. Okay, if I let's say I denote the policy in 2D space, let's say there are two, then what I am trying to say is, if this is my current policy, my next policy should be within some region of my current policy. It should not go too far from my current policy. So this region is what I am calling as trust region. Okay, so my new policy should be within my trust region of my current policy. I don't want to arbitrarily change it. Okay, so for that TRPO, how do you ensure that two policies are close enough? Do you know any metric? KL divergence. So KL divergence talks about how close two distributions are, right? A policy in a given state is a distribution for us. So TRPO method, what it tries to do is, it will try to constrain that the new policy, the KL divergence between my current policy and the new policy should be less than or equal to some threshold. That means it should not be too far. That is what the TRPO does. Like KL of, it will try to ensure that KL of pi theta k plus 1 comma pi theta k is less than or equal to some threshold. Okay, so that it will keep in the constraint. So there are multiple ways of dealing with it, but TRPO is theoretically good, but in practice it is complicated to implement. So PPO is like a practical version of TRPO. Okay, it is trying to maintain that, in essence, that it don't want to change the policy arbitrarily. It wants to change gradually, but it will do that. It will enforce that constraint in a different way. It will not put a hard constraint that the KL divergence between your current policy and the next policy is less than or equal to delta. It will not put such a hard constraint, but it will it will encourage policies to change gradually instead of changing abruptly. Okay, so let's see how exactly PPO is doing that. Okay,
So, like KL divergence is not symmetrical. So will that happen because the trust region should be kind of symmetrical?
I don't think there will be much issue with that, because a lot of places we are using KL divergence. So when you are talking about the KL divergence, one of the distribution, like it will be like expected x p log p by q or something like this, right? You'll have something like this. So this expectation is with what you are taking the expectation will create the asymmetry. So here we will take that expectation with respect to our current policy, because only with that policy you can sample. So there won't be any issues as such with asymmetry of KL divergence. Okay. So is this fine so far? Like yeah, everyone understood why this objective is making sense first of all? Because if the advantage is good, you want to increase the probability of that action. If the advantage is bad, you want to decrease the probability of that action. That much is clear. And we also understood that if you don't keep any other constraint, then it will go to some extreme policies. Like it will try to maximize some action fully and reduce the other action totally. But we don't want that. We want some gradual change in the policy. So for that, we just want to keep a cap on how much the policy can change. So let's see how PPO is doing that. So instead of the previous objective, what it is trying to, we'll just clip the policy. That's all. Like we'll just clip the objective. We won't encourage. Like if the objective is favoring, even if you take one here, then you will get the best objective, right? We want to just clip the objective such that it won't favor such extreme objectives. So there are two versions of PPO that are there in the literature. One is called penalty based PPO and the other one is called clipping based PPO. So what we are studying is called clip based PPO. Okay. So this is what we are studying here. So now I'll just change my objective like this. Min of this is my current objective, right? This is my current objective. I am just saying that I will clip this objective so that this ratio, if this ratio is, how do you understand whether a policy has changed a lot or not? This ratio will tell you, right? If this ratio is 1, what does it mean? If this ratio is 1, what does it mean? In that state action pair, there is no change in the probability. If this ratio is very high, there is a change. If this ratio is very low also, there is a change. So one way to prevent drastic changes in the policy is by restricting this ratio to be within certain range. That's what we are doing here. Okay. And this part will be there again, a by theta k of s comma a. Okay, this is my objective. Okay. And why am I doing min? Because I want the ratio to be at most this. Okay. So this is you will keep this in place of this. You just replace this part with that. Okay. The rest of the thing will be same. This part will be coming in front of that. Okay. You have to take expectation with respect to s comma a, that will be there, and you have to maximize over theta. So those things will come in front of this. Okay. So it's just that the objective has changed. Now you have to take expectation with respect to this, and where a comma s is sample based on pi theta k, and you want to do arguments over theta. This will be your theta k plus 1. Okay. All that I did was previously we had only this much, Now I just added this part and took a min of them to restrict the amount of change that is there in your policy. Now, although the expression looks complicated, if you just look at the two cases, what are the two cases that are possible for a given action state pair? The advantage is negative, the advantage is positive. So, if you just analyze those two cases, this objective will look much cleaner. Okay, although the effective objective looks like this, there are only two cases that are possible. If advantage is positive, what will this whole thing be equivalent to? If advantage is positive, which term will be maximum? Like which of these two will give the minimum if advantage is positive?
Right.
Right one. Because if you have only this and advantage is positive, it will try to take this to infinity or something like that. Because let's say this is like if this is very close to 0, then this will go as high as infinity, or if it has some fixed value, it will try to make this 1. Now the ratio itself can go tend to infinity based on how much this small this is. So this will get capped at 1 plus epsilon, right? Because the mean, you are taking the mean of these two.
So
Yeah.
what if the ratio is smaller?
Which one?
Pi theta by pi theta k? Then
No, this is objective, right? You are trying to maximize this. This is a running variable. So the whole optimization problem will boil down to this. Like if a pi theta k of s comma a is positive, then this whole thing becomes min of it is equivalent to maximizing this objective. That's what I am trying to say. So I am just trying to say that it is equivalent to maximize this quantity if a theta k of s comma a is positive. Okay. Anyway, this is just a detail. So you understood the high level idea, right? All that I am saying is you want to maximize that objective, but if you directly maximize it, you will run into issues. So we will clip that. That's essentially what we are trying to do. So without going into more details, I will just show you the pseudocode so that you understand you get a feel of this. So again, this OpenAI is a good source for this. OpenAI website is a good source for learning this. So this is our PPO pseudocode. So you initialize your theta parameters, the policy parameters arbitrarily, and you have another set of parameters. So what are these parameters useful for in PPO? What do we need in PPO? What is the objective having? What do you have in the objective? Advantage function, right? So you have to estimate the advantage function. So for that you have some set of weights phi, and for the policy network you have some set of weights theta. And what do we do? Like, this is the objective which we want to minimize. This is our objective, and what we do is, you start with your current policy parameter. You just run a lot of, you just interact with the environment with your current policy for a lot of episodes, for some number of trajectories. Okay, like a trajectory is like an episode. So you collect some trajectories by using your current policy. Okay, using that data that you got with respect to this policy, you have to estimate this quantity, because we want to take expectation over s comma a, where the data is taken with respect to theta k, right? The objective is having an expectation with s comma a sampled according to theta k. So to do this, you are just collecting lot of data using your current policy. Then you will know what s comma a pairs you will get in your current policy. Then in this objective, theta k is known, right? Your current parameters you know. So what are the only variables in this objective? So this expectation is with respect to what? S comma a over theta pi k, right? So you know all these values, right? How can you calculate this value? You have your current policy network. If you do a forward pass, you will get this value. So this value you know, and you have a advantage function also, like a neural network for advantage function also. If you do a forward pass for that, you will know this. So you can compute all these things. The only running variable here is theta, right? And you collect lot of s comma a pairs like this. For every s comma a pair, you can compute this quantity, right? For a given s comma a pair, can you compute this quantity or not? You just do a forward pass to your policy network, a forward pass to your advantage network, and then you can compute all these things. Now you get lot of such s comma a pairs. You run your current policy and generate lot of s comma a pairs and take an average of this expression over all of them. That will be your loss function. That's what you want to maximize. Okay, so that's what you will do in this pseudocode. If you see it, so they're generating a lot of trajectories with respect to your current policy, and they're computing the everything in this, and they're taking an average over those state s comma a pairs that you are getting. So they are collecting some let's say 10 trajectories. You have 10 trajectories. You are taking an average. How many? Let's say each episode is running for t time steps. Okay, let's assume that each episode is taking t time steps. Then how many s comma a pairs you will get? Number of trajectories into number of time steps. So you're just taking an average over all the time steps. You are getting lot of you are computing this expression for lot of s comma a pairs. You have so many s comma a pairs. You are just taking an expectation, sample average with all of them. That will be your objective. Now you will just do a gradient descent with respect to, or gradient ascent, because you want to maximize. You will just do a gradient ascent with respect to this loss function. Okay, and parallelly you will also train your advantage function. So we know how to train a value function, right? If you, for a given policy, we know how to train a value function. You just do mean square error minimization using SGD, right? So that's all you are doing. You are just maintaining an estimate of your value function. Based on that, you can calculate the advantage function also, and you do this gradient ascent with respect to this objective. So you can see that this is an on-policy algorithm. Why? Because to do this policy update, what samples are you using? So all these samples are collected from your current policy, right? So this is an on-policy algorithm. You are not reusing your previous data which was collected from the theta k minus 1 policy.